Welcome. In this video, we're going to solve a system of equations using an inverse matrix. So for our problem, we're asked to solve this system of equations using an inverse matrix in our technique. To begin, we would want to rewrite the system of equations in terms of a matrix. As we write this as a corresponding matrix, we would, for our first row of the matrix, look at the first equation. And then we're going to look at the coefficients in front of the variables. So in this case, there's a 1 in front of the x, a 1 in front of the y. Okay. After the equal sign, we see the value is 6. And that would give us our first row. Since this is two variables and two equations, we would get our second row to be this. So we get the coefficient in front of the x is 2. Coefficient in front of the y is 3. Okay, after the equal sign, we have 15. So this is a system of equations expressed as a matrix. And to really help us see what's going on with the idea of solving this system of equations using inverse matrices, it would be helpful to view this actually in terms of matrix multiplication. Whenever we write this expression, what's really going on is we're taking one matrix, 1, 1, 2, 3, and we're multiplying it by the coefficient matrix xy, and the result is 6, the matrix 6, 15. Okay. To make sense of it, let's actually do this matrix multiplication, and we'll see that we would get exactly this systems of equations. So we would take there's only one column, so we would take xy, kind of imagine bringing it over, and then we're going to multiply, so we would get, after this multiplication, 1 times x as the first entry, plus 1 times y. Okay. And then we would take this column again, multiply now by the second row of the first matrix, and we would get 2 times x. Ooh, sorry. Yeah. 2 times x plus 3 times y. As a matrix, this is equal to the matrices 6, 15. And here we can see the parallel between our original equation. In terms of matrices being equal, they're only equal if corresponding entries in the same location of the matrix are the same. So since this is a two rows by one column, these being equal means that 1x plus 1y has to equal 6, since these matrices are equal. Similarly, this entry must equal this entry, which would give us this equation. Okay. And we see we got back to our original systems of equations. So hopefully this just brief aside helps us realize why we can translate here, rewriting in terms of matrix multiplication, which we could then multiply to see we kind of get back to where we came from. So for now, I'm going to just erase this so that we can focus on looking at this idea. Now, focusing in this expression, our goal in solving the system of equations is, in the end, we're going to have x equals some number, y equals some number, okay? So we'd actually want to find what are the values that must go here to make this equation true. So we can see this as, let's call this first matrix, matrix A, times, we would call the second matrix, since it's our variable matrix, let's just call it capital X, equals another matrix, which we'll call B. Now, there is a rule that states if we have A times B, if matrix A times matrix B, matrix A times matrix X equals matrix B, then if we can find, so if A inverse exists, so if there is an inverse matrix, then we have that X is actually equal to A inverse times B. So what this is saying is if we could find the A inverse matrix from here, then if we multiply A inverse times B in the correct order, we would get the coefficient matrix that we're looking for, and we'd solve the system of equations. A few notes. Notice it's A inverse times B. Order of matrix multiplication is important. And then we look. This is the only thing that we don't know because we already know B. It's the matrix 6, 15. To find A inverse, we look at A and we see that it's actually a 2 by 2 matrix. Okay, we can find a 2 by 2 matrix using the following formula, which I'll write down. We can, if we know that matrix A is 2 by 2, then the inverse matrix is always given by 1 over AD minus BC, so AD minus BC, times, then you switch the entries on the main diagonal, and then you turn the entries on the off diagonal into just the opposite sign from what they were originally. For our problem, we have that we started off with matrix A being equal to 1, 1, 2, 3. So then by this formula, we know that A inverse must be 1 over, okay. Pause the video and write out the remaining part of this expression. And we would get 1 divided by 1 times 3 minus 1 times 2. All times we've switched the order of the main diagonal and we've changed the signs on the off diagonal to opposite of what they were originally. Okay, this would simplify to 1 over 1. So in this case, the determinant of this matrix was 1. Okay, 1 times this matrix is just this. So we would get A inverse is this. And remember, you can verify that this is indeed the inverse by taking the original matrix A, multiplying it by A inverse, and you should get the 2 by 2 identity in this case. Now, we're not yet finished with the problem. The reason we found A inverse is we want to apply this formula. So from our original expression, matrix A times matrix X equals matrix B, we know we can solve for matrix X by saying X equals A inverse, which we just found to be 3, negative 2, negative 1, 1, all times matrix B. Okay. Quick note on matrix multiplication. Remember, you can multiply matrices if the sizes of the two matrices follow the following rule. We would call this, since there's 2 rows, we would call it a 2 by 2 columns, 2 matrix. And this matrix here is there's 2 rows by 1 column, okay? We know that they can multiply if the number of columns of the first matrix equals the number of rows of the second matrix. Furthermore, we know the size of the resulting matrix will actually be a 2 by 1, okay? So we can just use that to check our work. So we should be expecting a 2 by 1 matrix, 2 rows, 1 column. So we would multiply these matrices. We would take the first column of the second matrix. Okay. Imagine we just lift that over and we would have 6 and 15. And we would get our first entry to be 6 times 3 plus 15 times negative 1. First row, first column, and then we would take this matrix, or this column, multiply it by the remaining rows of the matrix, so we would get 6 times negative 2 plus 15 times 1. All that's left to do is then simplify this, and we get that the variable matrix X equals 3, 3. Now we introduced matrices to solve the problem, but they did originally start as a system of equations, so we might rewrite our final answer as the variable x, okay, x and then y. X has value 3, y has value 3, or equivalently, the ordered pair 3, 3. And remember that you can always check the solution of the system of equations by plugging in the solution into both equations. And if both equations result in a true statement, then you've indeed found the correct solution to this system of equations. So let's just check our answers. X is 3, y is 3, so we would say 3 plus 3 does indeed equal 6, so it works in the first equation. 2 times 3 plus 3 times 3, that would be 6 plus 9, which indeed equals 15. So since this solution works for both equations, we know this is our final answer. Okay. Now, this does finish our review, okay, from all that we learned in 9.6 and 9.7 before spring break. So what I recommend before our next class period is that you should be sure to complete your homework from these sections. And then if you have any questions about this, please ask me via Canvas message, office hours, or in our class meeting. Okay, thank you.